Paleoclimatology is the study of changes in climate taken on the scale of the entire history of Earth. It uses a variety of proxy methods from the Earth and life sciences to obtain data previously preserved within rocks, sediments, ice sheets, tree rings, corals, shells and microfossils. It then uses these records to determine the past states of the Earth's various climate regions and its atmospheric system. Studies of past changes in the environment and biodiversity often reflect on the current situation, and specifically the impact of climate on mass extinctions and biotic recovery. History. The scientific study field of paleoclimate began to form in the early 19th century, when discoveries about glaciations and natural changes in Earth's climate past helped to identify the process of the greenhouse effect. Reconstructing ancient climates. Paleoclimatologists employ a wide variety of techniques to deduce ancient climates. Ice mountain glaciers and the polar ice caps ice sheets provide much data in paleoclimatology. Ice coring projects in the ice caps of Greenland and Antarctica have yielded data going back several 100,000 years over 800,000 years in the case of the EPICA project. Air trapped within fallen snow becomes encased in tiny bubbles as the snow is compressed into ice in the glacier under the weight of later years' snow. This trapped air has proven a tremendously valuable source for direct measurement of the composition of air from the time the ice was formed. Layering can be observed due to seasonal pauses in ice accumulation and can be used to establish chronology. Associating specific depths of the core with ranges of time. Changes in the layering thickness can be used to determine changes in precipitation or temperature. Oxygenating quantity changes in ice layers represent changes in average ocean surface temperature. Water molecules containing the heavier O18 evaporate at a higher temperature than water molecules containing the normal oxygen-16 isotope. The ratio of O18 to O16 will be higher as temperature increases. It also depends on other factors such as the water's salinity and the volume of water locked up in ice sheets. Various cycles in those isotope ratios have been detected. Pollen has been observed in the ice cores and can be used to understand which plants were present as the layer formed. Pollen is produced in abundance and its distribution is typically well understood. A pollen count for a specific layer can be produced by observing the total amount of pollen categorized by type in a controlled sample of that layer. Changes in plant frequency over time can be plotted through statistical analysis of pollen counts in the core. Knowing which plants were present leads to an understanding of precipitation and temperature, and types of fauna present. Palynology includes the study of pollen for these purposes. Volcanic ash is contained in some layers, and can be used to establish the time of the layer's formation. Each volcanic event distributed ash with a unique set of properties. Establishing the ash's source will establish a range of time to associate with layer of ice. Dendroclimatology. Climatic information can be obtained through an understanding of changes in tree growth. Generally, trees respond to changes in climatic variables by speeding up or slowing down growth, which in turn is generally reflected a greater or lesser thickness in growth rings. Different species, however, respond to changes in climatic variables in different ways. A tree ring record is established by compiling information from many living trees in a specific area. Older intact wood that has escaped decay can extend the time covered by the record by matching the ring depth changes to contemporary specimens. Using this method, some areas of tree ring records dating back a few thousand years. Older wood not connected to a contemporary record can be dated generally with radiocarbon techniques. A tree ring record can be used to produce information regarding precipitation, temperature, hydrology, and fire corresponding to a particular area. On a longer time scale, geologists must refer to the sedimentary record for data. Sedimentary content. Sediments, sometimes lithified to form rock, may contain remnants of preserved vegetation, animals, plankton or pollen, which may be characteristic of certain climatic zones. Biomarker molecules such as the organones may yield information about their temperature of formation. Chemical signatures, particularly Mg-Ca ratio of calcite in foraminifera tests, can be used to reconstruct past temperature. Isotopic ratios can provide further information. Specifically, the I-18O record responds to changes in temperature and ice volume, and the I-13C record reflects a range of factors, which are often difficult to disentangle. Sedimentary phases: on a longer time scale, the rock record may show signs of sea level rise and fall. Further, features such as fossilized sand dunes can be identified. Scientists can get a grasp of long-term climate by studying sedimentary rock going back billions of years. The division of Earth history into separate periods is largely based on visible changes in sedimentary rock layers that demarcate major changes in conditions. Often these include major shifts in climate. Chronology corals. Coral rings are similar to tree rings, except they respond to different things, such as the water temperature, freshwater influx, pH changes, and wave action. From this source, certain equipment can be used to derive the sea surface temperature and water salinity from the past few centuries. The I-18O of coralline red algae provides a useful proxy of the combined sea surface temperature and sea surface salinity at high latitudes and the tropics, where many traditional techniques are limited. Limitations: a multinational consortium, the European Project for Ice Coring in Antarctica, has drilled an ice core in Domes Sea on the East Antarctic ice sheet and retrieved ice which dates to roughly 800,000 years ago. The international ice core community has, under the auspices of international partnerships in ice core sciences, defined a priority project to obtain the oldest possible ice core record from Antarctica, an ice core record reaching back to or towards 1.5 million years ago. The deep marine record, the source of most isotopic data, only exists on oceanic plates, which are eventually subducted. The oldest remaining material is 200 million years old. Older sediments are also more prone to corruption by diagenesis. Resolution and confidence in the data decrease over time. Notable climate events in Earth history. Knowledge of precise climatic events decreases as the record goes further back in time. Some notable climate events: faint young sun paradox, Huronian glaciation, late Neoproterozoic snowball Earth, Andean Saharan glaciation, Carboniferous rainforest collapse, Permian-Euro-Triassic extinction event, oceanic anoxic events, Cretaceous-Euro-Paleogen extinction event, Paleocene-Euro-Eocene thermal maximum, Younger Dryas, the Big Freeze, Holocene climatic optimum, climate changes of 535 to 536, medieval warm period, Little Ice Age, year without a summer. History of the atmosphere. Earliest atmosphere the first atmosphere would have consisted of gases in the solar nebula, primarily hydrogen. In addition, there would probably have been simple hydrides such as those now found in gas giants like Jupiter and Saturn, notably water vapor, methane and ammonia. As the solar nebula dissipated, these gases would have escaped, partly driven off by the solar wind. Second atmosphere your next atmosphere, consisting largely of nitrogen plus carbon dioxide and inert gases, was produced by outgassing from volcanism, supplemented by gases produced during the late heavy bombardment of Earth by huge asteroids. A major part of carbon dioxide emissions was soon dissolved in water and built up carbonate sediments. Water-related sediments have been found dating from as early as 3.8 billion years ago. About 3.4 billion years ago, nitrogen was the major part of the then stable second atmosphere. An influence of life has to be taken into account rather soon in the history of the atmosphere, because hints of early life forms are to be found as early as 3.5 billion years ago. The fact that this is not perfectly in line with the 30% lower solar radiance of the early Sun has been described as the faint young sun paradox. The geological record however shows a continually relatively warm surface during the complete early temperature record of Earth with the exception of one cold glacial phase about 2.4 billion years ago. In the late Archean, an oxygen-containing atmosphere began to develop, apparently from photosynthesizing cyanobacteria which have been found as stromatolite fossils from 2.7 billion years ago. The early basic carbon isotopy is very much in line with what is found today, suggesting that the fundamental features of the carbon cycle were established as early as 4 billion years ago. Third atmosphere equals, the constant rearrangement of continents by plate tectonics influences the long-term evolution of the atmosphere by transferring carbon dioxide to and from large continental carbonate stores. Free oxygen did not exist in the atmosphere until about 2.4 billion years ago during the Great Oxygenation Event, and its appearance is indicated by the end of the banded iron formations. Before this time, any oxygen produced by photosynthesis was consumed by oxidation of reduced materials, notably iron. Molecules of free oxygen did not start to accumulate in the atmosphere until the rate of production of oxygen began to exceed the availability of reducing materials. This point signifies a shift from a reducing atmosphere to an oxidizing atmosphere. O2 showed major variations until reaching a steady state of more than 15% by the end of the Precambrian. The following time span was the Phanerozoic Eon, during which oxygen-breathing metazoan life forms began to appear. The amount of oxygen in the atmosphere has fluctuated over the last 600 million years, reaching a peak of about 30% around 280 million years ago, significantly higher than today's 21%. Two main processes govern changes in the atmosphere. Plants use carbon dioxide from the atmosphere, releasing oxygen. Breakdown of pyrite and volcanic eruptions release sulfur into the atmosphere, which oxidizes and hence reduces the amount of oxygen in the atmosphere. However, volcanic eruptions also release carbon dioxide, which plants can convert to oxygen. The exact cause of the variation of the amount of oxygen in the atmosphere is not known. Periods with much oxygen in the atmosphere are associated with rapid development of animals. Today's atmosphere contains 21% oxygen, which is high enough for this rapid development of animals. Currently, anthropogenic greenhouse gases are accumulating in the atmosphere, which is the main cause of global warming. Climate during geological ages. The Huronian glaciation is the first known glaciation in Earth's history, and lasted from 2400–2100 million years ago. The Cryogenian glaciation lasted from 850–635 million years ago. The Andean-Saharan glaciation lasted from 450–420 million years ago. The Karoo glaciation lasted from 360–260 million years ago. The Quaternary glaciation is the current glaciation period and begun 2.58 million years ago. Precambrian climate equals. The climate of the late Precambrian showed some major glaciation events spreading over much of the Earth. At this time the continents were bunched up in the Rodinia supercontinent. Massive deposits of tolites are found and anomalous isotopic signatures are found, which gave rise to the snowball Earth hypothesis. As the Proterozoic Eon drew to a close, the Earth started to warm up. By the dawn of the Cambrian and the Phanerozoic, life forms were abundant in the Cambrian explosion with average global temperatures of about 22 degrees Celsius. Phanerozoic climate equals. Major drivers for the pre-industrial ages have been variations of the Sun, volcanic ashes and exhalations, relative movements of the Earth towards the Sun and tectonically induced effects as for major sea currents, watersheds and ocean oscillations. In the early Phanerozoic, increased atmospheric carbon dioxide concentrations have been linked to driving or amplifying increased global temperatures. Roy et al. 2004 found a climate sensitivity for the rest of the Phanerozoic which was calculated to be similar to today's modern range of values. The difference in global mean temperatures between a fully glacial Earth and an ice-free Earth is estimated at approximately 10 degrees Celsius, though far larger changes would be observed at high latitudes and smaller ones at low latitudes. One requirement for the development of large-scale ice sheets seems to be the arrangement of continental land masses at or near the poles. The constant rearrangement of continents by plate tectonics can also shape long-term climate evolution. However, the presence or absence of land masses at the poles is not sufficient to guarantee glaciations or exclude polar ice caps. Evidence exists of past warm periods in Earth's climate when polar land masses similar to Antarctica were home to deciduous forests rather than ice sheets. The relatively warm local minimum between Jurassic and Cretaceous goes along with an increase of subduction and mid-ocean ridge volcanism due to the breakup of the Pangaea supercontinent. Superimposed on the long-term evolution between hot and cold climates have been many short-term fluctuations in climate similar to, and sometimes more severe than, the varying glacial and interglacial states of the present Ice Age. Some of the most severe fluctuations, such as the Paleocene-Eocene thermal maximum, may be related to rapid climate changes due to sudden collapses of natural methane clathrate reservoirs in the oceans. A similar, single event of induced severe climate change after a meteorite impact has been proposed as reason for the Cretaceous-Euro-Paleogen extinction event. Other major thresholds are the Permian-Triassic, and Ordovician-Silurian extinction events with various reasons suggested. Quaternary climate equals. The Quaternary sub-era includes the current climate. There has been a cycle of ice ages for the past 2.1 million years. Note in the graphic on the right the strong 120,000-year periodicity of the cycles, and the striking asymmetry of the curves. This asymmetry is believed to result from complex interactions of feedback mechanisms. It has been observed that ice ages deepen by progressive steps, but the recovery to interglacial conditions occurs in one big step. The graph below shows the temperature change over the past 12,000 years, from various sources. The thick black curve is an average. Climate forcings. The climate forcing is the difference of radiant energy received by the Earth and the outgoing long-wave radiation back to space. The radiative forcing is quantified based on the CO2 amount in the tropopause, in units of watts per square meter to the Earth's surface. Dependent on the radiative balance of incoming and outgoing energy, the Earth either warms up or cools down. Earth radiative balance originates from changes in solar insolation and the concentrations of greenhouse gases and aerosols. Climate change may be due to internal processes in Earth spheres and/or following external forcings. Internal processes and forcings equals. The Earth's climate system involves the study of the atmosphere, biosphere, cryosphere, hydrosphere, and lithosphere, and the sum of these processes from Earth's spheres is considered the processes affecting the climate. Greenhouse gases act as the internal forcing of the climate system. Particular interests in climate science and paleoclimatology focuses on the study of Earth climate sensitivity, in response to the sum of forcings. Examples: Merlin's circulation, life. External forcings equals, the Milankovitch cycles determine Earth distance and position to the Sun. The solar insolation, is the total amount of solar radiation received by Earth. Volcanic eruptions, are considered an external forcing. Human changes of the composition of the atmosphere or land use. Mechanisms equals, on timescales of millions of years. The uplift of mountain ranges and subsequently weathering processes of rocks and soils and the subduction of tectonic plates, are an important part of the carbon cycle. The weathering sequesters CO2, by the reaction of minerals with chemicals and thereby removing CO2 from the atmosphere and reducing the radiative forcing. The opposite effect is volcanism, responsible for the natural greenhouse effect, by emitting CO2 into the atmosphere, thus affecting glaciation cycles. James Hansen suggested that humans emit CO2 10,000 times faster than natural processes have done in the past. Ice sheet dynamics and continental positions have been important factors in the long-term evolution of the Earth's climate. There is also a close correlation between CO2 and temperature, where CO2 has a strong control over global temperatures in Earth history. See also, paleoceanography, paleothermometry, the study of ancient temperatures, paleotempestology, the study of past tropical cyclone activity, paleomap map of different ages and climates of the Earth, table of historic and prehistoric climate indicators. References. Notes Bibliography External links